And if you want to find that a copy of this script, it's going to be in the SPEDAS Bleeding Edge after tonight under the folder Projects, MMS Examples, Webinars. And you can find all of our other webinars, webinar scripts under that folder as well. And another thing to note is that the video recording will probably take a few days for it to be uploaded and processed to the full resolution. But it'll be on our YouTube page, which is just youtube.com/SPEDAS. And I usually Google to find it. You could just Google YouTube and SPEDAS, or yeah, YouTube and SPEDAS. So our tentative agenda, we're going to be covering essentially 5 topics. First is just an introduction to the FPI and HPCA load routines and their keywords. Then we're going to talk about generating the energy, pitch angle, and gyro phase spectra from distribution functions. And then we're going to plot some 2D velocity and energy slices from distributions using MMS part slice 2D. And then I'm going to show how to combine the time series moments and spectra plots with 2D slices. So that puts these 2D slices on a T-plot window. And then I'm going to talk briefly about visualizing the distributions in 3D using the IC3D tool. So just as an introduction to get started, introduction to the load routines. One important to note is to check the LASP website for information on the data sets. They have things like the release notes on the web, and it's important to read those release notes before jumping into any analysis. They have the data products guide right here, and then also the release notes. And so I just have a link to those for both instruments at the top of the script. And I think FPI, it's especially important to understand what you're seeing. They have a lot in their release notes. So for just a simple introduction to the standard keywords, the load routines all accept options via keywords, such as time range, which is just a list with a start and end time. They accept the keyword probes to specify probes. Most of the load routines have a default probe and don't load all of the data. So if you want all of the data from every spacecraft, or you want to change from the default probe, just use the probes keyword. And data type depends on the actual instrument. So to know the valid data types, you have to check the header of the load routine that you're interested in. So just for example, open MMS load FPI. So I have over here and look at the valid data types. So for FPI, it depends on the level. So quick look data has these. CITL doesn't take a data type, and then L1B data and L2 data has the DES and DIS distributions, and the DIS and DES moments. And this is also where you find the data rate keyword, so the valid data rates for each instrument. And so unless you're a team member, you're probably going to be using L2 data, which is the default loaded for each instrument. But we have all the other team-only data, the quick look data, the L1B, L1A. It's just a matter of setting the level keyword. And another useful keyword is the suffix. This will append a suffix to the variable names when they're loaded. So for instance, you want to load data from for 2 different days from the same instrument. You might want to append a suffix, otherwise your second load routine call might clobber the data loaded from the first load routine call. And for the plasma instruments, FPI and HPCA, we also have this center measurement keyword. So what this does is adjust the timestamps of the data so that the timestamp corresponds to the center of the measurement. By default, when you load FPI or HPCA data, the timestamps are actually at the beginning of the accumulation interval for the measurement. So if you want to, while the rest of the instruments are at the center of the accumulation interval. So when you load the data, you'll want to use this measurement or this center measurement keyword to center it to the middle of the accumulation interval. And So that's especially important if you're, say, calculating or creating plots with FPI data and FGM data, because you want them to be on the same timestamps, or at least the same epoch. And I should note that there's many more keyword options. These are just some of the most basic standard ones. It's important to see the header of the load routines that you're interested in if you're interested, or if you want to find more. So for example, we have keywords to do time clipping. One thing to note is that when you request data, we go out and find all of the files that have data within your requested time range, and then we dump all of the data from those files. So we don't time clip to your requested time range by default. This is for performance, because it can take a while to actually do that time clipping. So we have it as an option that's usually disabled by default. If you only want to load certain variables from the files, there's var format, which accepts Unix style wildcards. So it's like star for multiple characters and question mark for one character. We also have a keyword to return the CDF file names. And we have a keyword, we have several keywords for setting specific CDF versions. So you can learn, you can load a specific version with CDF version. You can load only the latest version in a series of files with latest version, the latest major version, that is with the major version keyword. So for example, this will load all the X files where the versions are X, Y, and Z. So if you want all versions, say 5 files, despite what the subversions say, you would set major version instead of latest version, because latest version is exact. And you can also specify a minimum version. So for example, only version 5 or later. And if you have trouble downloading the data from the last SDC, by default, all the load routines download the data from the Science Data Center. But there's also a keyword on all of the load routines called SPDF. So you just set that keyword if you want to load the data from SPDF instead. And the thing to note is that there's only public access data at SPDF. So the quick look data, for example, or levels outside of L2 aren't going to be available from SPDF. And I mentioned the center measurement keyword. So if you have a question about how many files you're going to download and how large of a download you're going to do, so if you request like a year's worth of HPCA data, you might want to set the available keyword, because this returns a list of all the files available for the requested parameters. And it will also tell you the output size, the download size. And so version numbers, this actually returns the version numbers of the CDF files. And always prompt. So by default, if you save when you first run the load routines, it's going to prompt you for a username and password. You just leave those empty if you don't have a username and password. You can just save it as an empty. But if you ever get a username and password, or if you accidentally save an incorrect password, you can use the always prompt keyword on any of the load routines to get that prompt back. And so another warning, we are recording this. I mentioned it earlier, but I want to mention it again for the people who just joined. We are recording this for the users who can't make it, and we're going to upload it to YouTube. All right, so before jumping into the FPI and HPCA load routines, I wanted to show another routine called MMS Event Search. What this does is allow you to search the MMS events database. It's created by the Scientist in the Loop software. So whenever a CITL creates or marks an interesting time in the Scientist in the Loop software, it updates a database at LASP that provides all the MMS events. So best way to, and this provides access to that database. So the first input is really just something that you want to search for, and then you can also give it a time range. If you don't give it a time range, it gives you all the it actually searches the description for all the time or all of the events that have that description. So let's go ahead and run it. And I should maximize this. So the first time that you run this, it's going to take a minute or two to actually download the database, but subsequent calls should be a lot faster because it just uses the database that's already in memory. So you can see it's downloading the database. And we're going to search for the word current and within this 50-minute time frame. And I pulled this time frame from a paper that Ty Fan published in Nature a couple years ago. So I know there's something interesting going on there. Again, this building the event index, it only happens once in the session. So you can do multiple calls to MMS Event Search with, and the second time will be a lot faster. While that's searching, and give some, and this routine accepts more keywords that we're not showing here. You can, for example, return all the descriptions for all the found events, turn the authors, the start times and end times for the events. And you can also turn on a keyword that says quiet that disables printing off what it just printed here. So you can see Ty Fan set the submitted these through EVA, which is the MMS Science in the Loop software. And the description is turbulent magneto sheath with sharp current sheets and has the time selections. And so another useful routine is finding the actual burst segments in this time range. So this is SPD, MMS load BSS. I think it's burst segment status. And we're going to set the data type to burst and tell it to include the labels. So show what that means. So I went ahead and loaded the burst segment statuses. And then we're going to finally use MMS load FPI to load some DES and DIS moments data. By default, I think FPI loads data from probe 3. Most other instruments load probe 1 by default. I think all but FPI pretty much. And I'm going to set the data type to both the DES and the DIS moments and use the same time range at 50 minutes. And going to tell it to actually do the time clipping and center the measurements. So it loaded the data and now it's time clipping. And so then we call tplot on, so this is the burst segments. It's a bar, it should create a bar that just shows the burst segments over time. And then we're also plotting the DIS number density, and the DES number density, and then the DIS energy spectra and the DES energy spectra. So that's what was created here. Let's minimize that. So there are burst intervals or burst data up until just before it's like 9:10, and then another burst interval around 9:22 or so that goes past 9:30. And this include labels, and this call added the label here, burst. Another option to the data type here is fast, to load the fast segment intervals. So that would just be a straight line across here, since we have fast segment data or fast survey data for the entire interval that we're showing here. And since we use time clip, we're getting exactly the 9 o'clock to 9:50 data. There's no data loaded outside that because we did the time clip. So if you want to change an options for a panel, you just use the options function. And for example, we're calling options on the ion number density here, setting colors to 0. So this is colors is based on the index for for the current color table. And 0 in our color table is black. So they should change this DIS. This is the top panel here, from green to black. So we set that option, and then we do an empty call to tplot, which replots the data with the updated metadata. So notice that the DIS density is now black. And so FPI also has these data quality flags bar that point you to potential problems with the data quality. So those load automatically with the data. So if you just do a tplot name, you should see that we have the error flag bars. So to go ahead and add those to the plot, you just call tplot, and calling it with the add, calling tplot with the add keyword set actually adds whatever the plot you're looking at or whatever variable you specify to the top. So notice it added the error flag bars to the top. And there's apparently an issue with the data here right after 940, or potential issue. And so, and to see more about these, we just go to this on the web. So it should be, oh, that might be behind a password. It should be in or they should be in the README notes as well, though. And so to load HPCA data, again, it's just MMS_load_HPCA, and you give it the data type. And notice that in this case, the data type for HPCA moments data is different since it's a different instrument. For HPCA, it's just moments. And again, we have the center measurement keyword to actually center the measurements to the middle of the accumulation interval. And then we're going to call tplot on the H plus number density from HPCA. And again, the add keyword adds that number density to the top panel. So now we have the HPCA number density for H plus. And another data type for HPCA is ion. So this is the distribution functions, the flux. So you just specify data type equals ion, give it the time range, probe. And again, we're doing time clipping and centering the measurement to the middle of the accumulation interval. And the ion data is going to take a little bit longer to load because of the larger file sizes. And the important thing to note is that the HPCA ion data is multidimensional. So some of the variables are a function of both energy and angle. So to find the full omnidirectional spectra, you have to sum over some specified field of view, which for omnidirectional is 0 to 360. And then you have to average over the spin to get the full omnidirectional spectra. And you do that with these routines, MMS HPCA count A nodes, and then that does the summing over the field of view. And then you do MMS HPCA spin sum. And by default, the spin sum calculation will sum over the spin. But there's a keyword average that allows you to do spin averaging instead of spin summing. So we're still loading HPCA ion data. All right, so that now that we have the ion data, we can do a tplot names to list the new variables. You can see it loaded the phase space density, data quality bar, and the flux for all the different species for HPCA. And so now we'll create the omnidirectional spectra, summing over the full field of view, and then averaging over the spin. And so when you first, when you run this, the sum over the full field of view, it creates a variable here. Let's them. It creates the variable with the elevation and the angles. And then when you call the spin sum, it creates new variables with the suffix _spin applied. So these elevation 0 to 360 spin function or variables are the omnidirectional energy spectra. So just as an example, we could say t-plot add that to the top. Now we have the HPCA omnidirectional spectra added to the top for this time range, just above the HPCA density for H+. And so to actually get the data out of variables and the metadata out of a t-plot variable, you just use get _data and set the data keyword for the data for the variable that you want to return data for, and then the delimits keyword for, so the delimits are the default metadata, which are usually set by the load routine, and the limits are the metadata that are set by the user during the session. So if you use options, like when I changed the color using options up here, it updated the limits, not the default limits. So that allows you to find metadata that's, for example, from the CDF is going to be in the default limits, but metadata during your session are going to be in the limits. And so, of course, data is just going to be in D here. So I ran help on D and notice that the time data are stored in X. And then the flux data are actually stored in, since we're looking at flux here, stored in D.Y, which is a function of energy. And then the energies themselves are stored in D.B. So you can print out the energy table just by printing D.B. That gives you the full energy table. And if you want to see the CDF metadata, you just run help on metadata, which is returned by delimits. Actually do that next. So we can go ahead and the variable attributes data. One thing that I look at frequently is just CDF. So I usually use help on CDF, and then you can look at the variable attributes by VAT. That gives you all the variable attributes from the metadata. And there's also GAT for global attributes, which comes from the full file. And one thing to note when you look at this plot is that the units are actually different from for HPCA and FPI. So to do a simple calculation, since we already pulled out the data from HPCA, we can convert to energy flux units just by looping over time and multiplying each data point by the energy. So that's what this example does. Close mail client. All right. And so I just looped over every time, created a new variable called eflux that has the data at each time multiplied by the energy, say the energies. And one thing to note is append array. It's a SPEDAS tool that allows you to essentially create a new array and then append to it. So if this eflux wasn't defined beforehand, it creates that eflux, and then at each time it appends the next timestamp, which would be or the next data point. So it can run help on eflux and see it's got 300 times and then 63 energies. And we can then store the data back into the tplot variable using store data. So this is the opposite of get data. It allows you to actually create a new variable from some data, as well as it accepts delimits and limits as well. But in this case, we're creating with no metadata. So we're just calling store data with X specified as the times, and then Y as the energy flux that we created up here. And then the energy table is just, again, D.B. You can see it created that variable. So in this next plot, we're going to create a plot of the DIS energy spectra, the HPCA energy flux, and then number density for DIS and HPCA. And notice that since we didn't set the metadata in the call to store data, the HPCA energy flux is currently line plots at each energy. So again, you just use options to set options for your newly created variable. So what we're going to do is set spec equals 1, that turns it into a spectrogram, and then y log, which converts the y-axis to logarithm scale, and z log, which turns the color bar axis to logarithm scale. Then we set the z title, and then y title, and then the y subtitle, which is just below the y title. And we just do an empty call to tplot, and that replots the data with the updated metadata. So you can see now we have the FPI ion energy spectrum on top, and the HPCA H+ energy spectrum just below that. And another useful aspect to get data and store data is that it actually supports adding error bars. And so to add error bars, so in this case, the ion moments data for number density actually has error bars with it. So we have to pull the number to create a new variable with error bars. You just pull the data out and then pull the error bars out of this other variable, and then call store data to create a new variable. And I named it with error, so with error bars. And the big difference here is that I'm now specifying a dy that has the error bars. So we have X with the times, Y with the number density, and dy is the actual error bars. And I multiplied the error by 100, so it shows up on the figure here. Otherwise, I think the errors are pretty small in this case. So we can then replot, and instead it should be the same plot, except now we have error on the DIS number density. So there's actual error bars, and it's kind of hard to see. So we're going to zoom into a part of the figure with the T-limit option or function. So you just give it an array, a 2-element array with the start time and the end time that you want to zoom into. So we're going to zoom into 2 minutes. So 9:02 to 9:04. And you can see now the error bars are pretty clear on the DIS line plot. And another useful tool, so most of tplot has to do with these time series plots, but sometimes you want to create an energy spectra for a single time. So to do that, you run this routine flatten_spectra. And by default, it allows you to select a time on your figure once you run it to create that spectra plot. And so let's just take that time. And so I created a new figure, and it has also I gave it the bar keyword. What this does is add a bar to the tplot window where the energy spectra was actually created. And I told it to use a logarithm axis on the X and the Y. So this is the specific time that I clicked on, and it has the spectra for all the spectra variables in the panel, and it ignores the line plots. And so it created EV on the bottom, and then the energy flux on the y-axis. And so there's also another tool for creating multiple finding the spectra at multiple points. So it's called Flattened Spectra multi. And the first argument, really the only required argument, is a number that shows how many, or tells how many spectras you want to generate. So I told it 4, so I had to do, allows me to click in 4 places. So let's just click in 4 places. And added bars at each place. And it should have created a new window. Yep. And now the legend, I also gave it the keyword in this option, or in this case, legend left, to tell it to plot the legend on the left-hand side. By default, it puts it on the right-hand side. And the colors correspond to the different times. And another useful thing is if you want these plots on the same units, Flattened Spectra also has keywords to change the units internally. So in this case, we're plotting the ion energy spectra on top and the HPCA energy spectra on the bottom. But again, these are different units. This is an energy flux and this is just flux. So if you were to create a Flattened Spectra plot on this, it's going to have different units, and it should warn you as well that the units are different. But we have these keywords 2 keV that converts, so that converts the energies to keV, and 2 flux will convert the data values to actually flux. So go ahead and create another. And so here you see the data were converted to flux and the energies were converted to keV. And so another useful tplot tool is to create figures with panels that contain different types of variables. So you might have a spectra and then a line plot on top of a spectra with a different axis. So to do that, you call this function tplot multi-axis. So the first argument is a list of the variables with the axes on the left-hand side. And the second argument is a list of the variables with the axes on the right-hand side. And then you tell it, the last argument is where you put the plots. So in this example, we're going to plot the energy spectra for FPI, and then the energy spectra for HPCA, and then the number density over each of those. And so notice in this plot now, the y-axis on the left-hand side is for the energy spectra, and the y-axis on the right-hand side is for the number density. And we've overplotted the lines on top of the spectra. And so in this case, since the lines have labels, the labels are still being plotted, and they overlap with the axis. So that's the y-axis, or the y titles. So to turn those off, you just set the options and to an empty string. And that tells it to turn off the labels. So we're gonna go ahead and replot, and now the labels are gone. And you just have the y-axis for the energy spectrum on the left and the y-axis for the line plot on the right. And notice that the color bars disappeared. Technically what happened here is they got pushed off the screen. So if you want to get those color bars back, you just call tplot underscore options. And tplot options is like options, except instead of only applying to one panel, it applies to the whole figure. So if you want to increase the X margin, you just, so this is the left-hand X margin, and this is the right-hand X margin. And then you can call tplot multi-axis to recreate the figure. So when I increased the X margin here, it moved the margin just enough to include the color bars again. So you can see we have the color bars back. And so one more useful tool for loading and creating FPI and HPCA figures is our are these MMS FPI and MMS HPCA. So these create angle energy plots. And for FPI, it also creates pitch angle energy plots. And this is for the time closest to the requested time. So if you give it 9:03, it finds the time that's closest to that and then plots the angle plots for them. So internally, it's going out, loading the data, doing all the calculations, and then creating the figures. So you can see we have the zenith flow angle as a function of energy. We have azimuth flow angle as a function of energy. And we have energy as a function of pitch angle, and then zenith flow angle versus azimuth flow angle. And thing to note about this is that on the zenith flow angle by azimuth flow angle, that is the full angle plot, we include pitch angle contours as well. And there's a keyword to turn that off. There should be several keywords in there. If you're interested in creating these, you should check the header for all the various keywords. And so we also have HPCA angle. And the thing to note about this is that it does the angle plot for 1/2 spin closest to the input time. So half the spin is going to be missing here. And it's going to be around 9 seconds of data. 9 to 10. But just like with the FPI angle, it goes out and downloads the data and creates the plots. And this one's missing the pitch angle energy plots. We don't have that for HPCA here. But it creates a zenith flow angle versus energy, and then the azimuth flow angle versus energy, and then the zenith flow angle versus the azimuth flow angle. And notice that half the azimuths are missing. That's because it's only a half spin. So it doesn't have the full angular range included in these angle plots. And so that's the basics of loading the HPCA and the FPI data. So I guess we could go ahead and jump into the MMS part get spec, which is generating the energy and pitch angle gyro phase, the actual spectra from the full distribution functions. We have a bunch of crib sheets that include how to do these calculations. I think there's an advanced crib sheet to do even more. I was suggest taking a look at the get spec crib sheets under the advanced folder if you want to find more details here. And so I also shortened the time range here to 5 minutes to try to limit the time it takes to do the calculations. So let's go ahead and we'll just go ahead and create some energy spectra. So it's just a matter of calling MMS part get spec, and you give it the time range, species, and by default it uses FPI data. So if you don't specify an instrument, it's going to use FPI. And I think by default it does all probes. So you probably want to specify a probe if you're just looking at one spacecraft. And it has you have to again set the center measurement keyword. I'm just using center, but internally it's the full center measurement keyword to center the measurements to the middle of the accumulation interval. And so when this routine finishes running, it creates so essentially in the FPI distribution data, they have these variables that are just DIS, dist, and then the data rate. And so when you generate energy spectra or pitch angle distributions, it creates variables with a suffix, for example, _energy, _PA for pitch angle. Another one is _gyro for the gyro phase spectra. And just like with the load routines, there are a lot of keywords here. So you really want to check the header of this routine to see the full power of it. And it also accepts the keywords for MMS part products, which is so internally what MMS part get spec does is load all of the support data and then call MMS part products with all the data or all of the options that you supplied. And so you want to check the headers of both of those routines for available options. And so we created a plot here. You notice that it created several new variables, one energy spectra, one theta. So this is the angular spectra with theta. And this is the phi spectra. This is the pitch angles distribution, and then the gyro phase spectra. And then we just called tplot on the energy spectra and the pitch angle distribution. And so you have the energy spectra on top and then the pitch angle distribution on bottom. And we're still zoomed in from that T-limit call earlier to 2 minutes of data. So it didn't show the full 5 minutes, but it should have done the calculation for the full 5 minutes. And so in the next example, we call get spec with the instrument set to HPCA and the species set to H+. And again, for probe 1, and that should do the HPCA calculations. And internally, the HPCA measurements should automatically be centered because there's an assumption when we load the data in that the HPCA measurements are centered. So we have to center them prior to doing the calculations here. And just like with FPI, it goes out, downloads the data, downloads the support data, and then calls MMS part products to do the actual calculations. While that's finishing, I can show some more of the keywords here. So we have keywords for specifying the output units. Give it energy range, give it a phi range, give it a theta range, a pitch angle range to include a gyro phase range, and finish doing the calculation. In this case, it took the PSD variable and it just appended an underscore energy to the end for the energy spectra. And I called tplot on that new variable and added and did the add keyword to add it to the top. So now we have the HPCA energy spectra on top. And again, it created the angular spectra and pitch angle spectra as well. I showed that energy keyword. So if you want to do the energy spectra calculation directly from the distribution function and limit the energy to some range, in this case, we limit it from 100 EV to 10,000 EV, so 10K EV. And specify the instrument is FPI, and species is just ions. It should do the calculation. This time limiting it to just these energies. And you can see on the figure over here, without specifying the energy range, it includes the full energy range. And again, in the header, it shows You can limit the other things outside of the energy range as well, like the phi, the angles, theta angles, the pitch angles, and gyro phase. And so if you want to speed this up a bit, you can, and you're only interested in one of these, like the energy spectra or the pitch angle distribution, you can set the outputs keyword to just energy or to just energy and pitch angle. And these routines can also calculate the moments, that we're not doing that here. It's just setting the output to moments. And I'm going to show the multi-pad keyword in a few minutes, or option. So here's the, this time instead of doing add, we just created a new plot with the energy spectra that we just calculated. And this time notice that it only used data from around 100 eV to around 10,000 eV. The same thing works with HPCA. So again, just give it all the same options as before, except now you're setting the energy to 100 eV to 10,000 eV. And I'm sure this routines also accept the suffix keyword. So if you want to generate with different, the options with different different variable names, just append a suffix to the end. Like say, specify different energy ranges. You'll have to just specify those energy ranges as a suffix on the variables. Otherwise, subsequent calls will overwrite your variables if the variable names are the same. And so this time we're adding the HPCA H plus energy spectra to the top, just again with the add keyword. And so we have the HPCA energy spectra on top. And so there's also a units keyword to specify the output units. So I think by default it does energy flux, but you can also specify flux. So in this example, we're not limiting the energy range, but we are specifying the output units of flux instead of energy flux. And then we're going to plot that data alongside the spin average omnidirectional spectra that we calculated earlier directly from the ion flux. And so now it's got all the support data loaded and it's doing calculations. And now we have so on top, we have the energy spectra that we just calculated in flux units. And then on the bottom, we have the omnidirectional energy spectra that we calculated earlier using the MMS calc A nodes and spin averaging. And so another useful feature is, so with these angular plots, for instance, the phi spectrogram and the theta spectrogram, sometimes you want to know the direction of the B field and the spacecraft RAM direction. So there are keywords that'll actually add those to the variables. So the spacecraft RAM direction would be X's, and the B field direction will be plus for the plus direction and minus for the minus direction. And you just add those keywords, add B field dir and add RAM dir to add the directions to the variables. And this time we're not creating the energy spectra or the pitch angle distribution or the gyro phase distribution. We're just creating the phi and theta spectrograms because we're specifying that output keyword. And so notice that it took a little bit, it was a little bit faster this time because we just limited it to those two calculations. But when you include a phi and a theta here, it generates the phi and the theta spectrograms, but it also creates these new variables with BV. So that's the B field direction and the RAM direction. And so in this example, we plotted the theta spectrogram on top. So it's the energy spectra as a function of theta, and then spectra as a function of phi on the bottom. And notice that there are these X's and pluses. So the X is the spacecraft RAM direction, and the plus and the minus are the B field direction. And so by default, we have a default interval here that we plot these. You could change this with the dir interval keyword. I think with survey B field data, we do it once every 60 seconds. And with the spacecraft RAM direction, we just use the once every 30 seconds. But if you update it to dir interval, this is in seconds. So it's going to plot the B field direction every 10 seconds. But I don't think it won't use the RAM direction. It'll still be 30 seconds for the RAM direction because that's the resolution of the data. If you go below the resolution of the data, it doesn't interpolate. It just it uses the resolution of the data instead. So notice there's more B fields added to the figure here. So the plus and minus should be every 10 seconds or so. And so earlier I mentioned, I showed that there was an option called multipad. What this does is sometimes you want to, doing the pitch angle distribution calculation for a bunch of different energies can take a while. So instead of spending all that time generating or having a bunch of calls to MMS part get spec to generate various pitch angles, you can create essentially a pitch angle distribution as a function of for each energy. And then we have routines that allow you to do summing over energies. So you can call it MMS part gets pad. And I'll show how that works in just a second. So in this case, our output variables are the energy, the pitch angle distribution, the gyro phase distribution, and then multipad. And I'm doing a burst interval that's 1 minute long. I guess while that's still generating, we can open the MMS part get pad routine. And essentially, this allows you to quickly generate pitch angle spectrograms from the multipad output from MMS part get spec. So MMS part get spec will create a new variable that has the pitch angle distribution of various energies, and then you give it you call MMS part get pad with the energies you're interested in, and then it just sums over those energies and creates new variables with different energy ranges. And this looks like it's going to take a lot longer than it did yesterday. But once this calculation is done, and then you call MMS Spark get pad, it creates a new variable every time, and it appends the energy range to the suffix. So in this case, it'll do 0 to 100 EV, then 100 to 1,000 EV, and then 1,000 to 10,000 EV, and then say 10K EV to 20K EV, then 20K EV to 30K EV. And so we also have keywords for subtracting the bulk velocity, subtracting the error. This is an MMS Spark get spec, and subtracting the spin tone from the bulk velocity prior to doing the calculations. I think I'm going to show some of these in the slices, but not necessarily. Oh no, I have an example for these down here as well. And I guess while we're waiting on these to generate the multi-pad distribution, I should mention that if you generate the spectra or the energy spectra, and you should check the output against the options or the data products provided by the team. For instance, for FPI, they include energy spectra, the omnidirectional energy spectra in their moment CDFs. And so if you do it with no options, it should produce essentially the same distribution with maybe precision issues, but or differences due to precision. But for the most part, they should match. If they don't, you should really look into why they don't. So I know there are cases where if you generate the moments with MMS Spark get spec, they don't match those provided by the team, and those provided by the team are really the science quality ones. So you should try to understand what's going on there before and make sure that they actually match, that you can generate the same ones provided by the team before publishing. And this calculation was a lot faster yesterday. I think whenever people are watching, my computer slows down. But it's almost done. All right, so notice again, it created the energy spectra, created the pitch angle distribution, and then it created the gyro phase, but it also created this variable pad that ends with underscore pad. And so if we call get data to pull the data out of that variable, you see this is the pitch angles as a function of angles and energy. So there are multiple V's. So V1, that's the energy, and then V2 should be the angles. And it's also a function of time. And so you can't actually create a plot of this. If you do, I think it might use the bottom energy, but you really don't want to create a plot using the pad variable. You'll want to, so notice I updated the time is different here. We were looking at 2 minutes of data. Now we're just looking at the very end here of those 2 minutes. So if we call T limit, we can zoom in to that 1 minute. Again, just zooming into the the time range of this burst mode calculation that we did. And we have the FPI energy spectra on top, the pitch angle distribution, and the gyro phase distribution. So now we can call MMS part get pad, which uses that underscore pad variable. And notice how quickly that was. We generated the pitch angle distribution for 5 different energies, 5 different energy ranges, just with that, just with those 5 calls to MMS part get pad. And so now we can call tplot to actually plot those. So we have the 0 to 100 eV on top, the 100 eV to 1 keV below that, and then 1 keV to 10 keV, and 10 keV to 20 keV, and 20 keV to 30 keV. And another thing to note, I showed flattened spectra earlier with energy spectra. It also works with pitch angle distributions. It works with any kind of spectra. So in this case, we're going to call flattened spectra again. This time we're only setting Y log. We can pick a time to create a spectra. So now you can see, since these are the y-axis on the spectra are angles. So for the pitch angles, it added, so the x-axis in this case is pitch angle. And then of course the z-axis here is the energy range, or the flux. So in this case, the y-axis is the flux. So this is essentially the pitch angle distributions for this time where we added the bar. And again, the variable names are the different colors. And there is a custom, if you have more, it should be a custom or a color keyword that allows you to set the colors. Eventually it wraps around. So there's a colors keyword to change. So if you have more than 5 or more on a figure, then you might want to set colors to custom colors. And so notice down here, we don't have the degrees, the units specified for the x-axis. That's because that is taken from the Y subtitle on these figures. And so if you want to set that, you essentially just call options, give it the variables, and then set the Y subtitle to degrees. And then call tplot to replot. And notice that now the Y subtitle has degrees. And then if you call flattened spectra again, it should update this the units down here. And another useful keyword here is replot. So by default, if you don't call it with replot, it'll make you select times. If you previously called flattened spectra, you can just call replot and it'll replot at the same time, but with the updated metadata. So it went ahead and used the exact same time, and now it has the degrees for the units along the x-axis. And I definitely suggest checking, if you use flattened spectra at all, check the header, because there are all kinds of options here. Outputting the data in PostScript, PNG files, specifying, again, I showed 2 keV and 2 flux earlier, giving a file name prefix, the ranges, disabling the legend. And there should also be there's also a way to set the custom legend titles, but I'm not seeing it right now. You can also change the character size of the window. I'm not saying, you can set the time instead of clicking on the window. You can also set the time using the time option or a T range. So there's lots of options there, and there's a crib sheet for flattened spectra in our examples folder. I'm not sure if it's under the basic or advanced, but it should have flattened spectra in the name. It shows a bunch of different options. And so another example, MMS part get spec, we have keywords specifically for some FPI stuff. I think subtract bulk subtracts the bulk velocity prior to doing the calculations. Subtract error, subtracts the distribution error. So if you load the distribution functions, you'll also get this distribution error estimate. And yeah, there's also a subtract spin tone, which subtracts the spin tone. If you load the FPI moments data, it also loads the spin tone estimates from the velocity. So if you use this keyword, it'll subtract the spin tone from the bulk velocity prior to doing the bulk velocity calculations. So hopefully this doesn't take too long. So you can see internally it's telling me now that it's using the bulk velocity just for the bulk velocity subtraction. It's a good chance to look at crib sheets for more. Let's just go to our examples folder. So there's the basic examples, advanced examples, and then we have quick look examples and webinars. The webinars folder is where this script is going to live after today. And you can see previous scripts that we've gone through in the past. So, but for MMS part get spec, that's almost certainly under the advanced folder. So we have the crib sheet for the basics, and then there's another crib sheet called advanced that shows more advanced examples. So for example, options where you limit the energy range, limit the pitch angle range, change the output units, all those are considered advanced examples. And here's the part get spec, the simple examples. And I mentioned that there's a flattened spectra example. I think that's under basic. Yeah, so it's MMS _ flatten _ spectra crib. So it shows how to do, yeah. So, oh yeah, to set the legend names, you just set the legend _ name option on each variable. So it's not a keyword, it's just setting that legend _ name option. And that'll change the legend name to whatever you want it to be. And so we also have examples showing how to save the files as PNGs, PostScript, and then converting to KEV. And so in this crib sheet, we also include EIS in the figure as well, because I think EIS is actually in KEV. So if you plot EIS, FPI, and HPCA, you'll probably want to do 2 flux and 2 KEV to make sure everything's on the same. Everything has the same units and everything's on the same scale. So here's the energy spectra with the bulk velocity had the spin tone subtraction applied, the distribution data had the error removed, and then the distribution data, we subtracted the bulk velocity prior to doing the calculation. So I guess next we can go ahead and jump into creating 2D velocity energy slices from the distributions. So just like with MMS part get spec, we have a routine called MMS part slice 2D. So that generates 2D slice images. And again, just like MMS Parquet Spec, what it does is goes out and loads the data, loads the support data, and uses our slice 2D routine internally to actually create the slices. So let's go ahead and just do some calculations. So I gave it so in this case, we're doing FPI, ion data for probe 1. And I gave it the time. And the thing to note here is that it uses the time closest to this time. So this time doesn't have to be exact. And I changed the date because I changed the date from above because this is an interesting time for plotting slices. There's a bidirectional field aligned beam in this at this time. So I think it makes a good example. So just like with Parquet Spec, you can limit the energy range for the slice, except instead of it being energy this time, it's just E range. And that's to match our the way keywords are done in Slice 2D or SPD Slice 2D. And I should note that by default, we use geometric interpolation. Each point on the plot's given the value of the bin that it intersects. But in this case, I'm using 2D interpolation, which is data points within the specified theta as the axis range are projected into the slice plane and then interpolated. I'm using 2D interpolation in these examples because it's a whole lot faster to create figures. But by default, it's going to use the slower geometric interpolation. And so I set the interpolation with this keyword at the end, 2D interp. And one other thing I should mention is that again, I'm only showing a limited number of the options, but there are bunches of options to this routine to create these slices. So check the header for all the options and their defaults. And so this is for the full energy range. If we want to limit the energy range 0 to 300 EV, you just set the E range keyword. And by default, it creates a figure. It's Vx along the bottom and then Vy along the y-axis. So this is just 0 to 300 EV. So much more limited energy range than the previous plot. And you can change the rotation with the rotation keyword. And here are the options. So in this next example, we're going to limit the energy range and we're going to put it in a field aligned coordinate system. But the other options should all be the same. So we just specify the rotation equals BV. And I copied and pasted these descriptions from the header of the file. So you can always just check the header for what these actually mean. But for BV, the x-axis should be parallel to the B field, and the bulk velocity should define the xy plane. Right. So now the bulk velocity defines the xy plane, and the x-axis is parallel to the B field. And again, this is just FPI ion data with the energy range limited from 0 to 300 EV. And so if you want to do HPCA, you just set instrument equals HPCA and species to H plus. Though I think internally, if you don't specify H plus as the species, you just tell it HPCA. It should know to use the right species for HPCA, or you should default to H plus. But all the other options, the probe, 2D interpolation, the time are all the same as the previous FPI example, and same rotation, BV. And note that there's a field aligned beam. And again, bidirectional field aligned beam for HPCA. And just like with MMS Parquet Spec, there's a units keyword. By default, it's plotting the distribution function. So it's just plotting the distribution function, but you could tell it to plot units of flux. I just say units equals to flux. And this is going to be FPI again, because we didn't specify an instrument or a species by default. These routines use FPI. So you can see it's loading the FPI data. And so now instead of being in units of distribution, the distribution function units, it's units of flux. Again, you can see the bidirectional beam. And so what happens if you do this for a time that's in the solar wind? So I found a time in the solar wind, which is this time. I'm using probe 4. So it should load probe 4 and it should do ions. And again, this is FPI and with 2D interpolation. So I think, so you notice that it's off 0 here. It's because I think the X component, it's Vx versus Vy. So I think the X component of the solar wind is this offset here. So you can subtract the bulk velocity, just like you could with MMS part get spec. And if you subtracted the bulk velocity, theoretically, it should move this to the center of the figure, since we're essentially subtracting the solar wind velocity prior to creating the slice. And definitely moved it over. And just like as before, you can subtract the error, the distribution error from the data prior to creating the slice and the bulk velocity. So I think this will put it more towards the center. And I think the reason it's not putting everything exactly at the center is because essentially when you're in the solar wind, velocity really is the dominant thing that you're subtracting it. And when you subtract it, there's not much data left there to work with. But now it's almost dead on center. And again, if there are so many options to these routines, you pretty much always have to get started by looking at the header and going through the options, try to figure out exactly what you want to do. You can apply custom rotation matrices to these slices. You can apply displacement vectors, add contours, do contour overplots, do the sun direction, plot the bulk velocity on a figure, plot the B field on the figure. Of course, there's options for changing the contour lines, the character sizes, X and Y range. There's so many options here. You can export it as a PNG file. You can export it as a PostScript file. So outside of the header, the best place to go for more examples is definitely the advanced folder. And you just find the MMS Slice 2D FPI code for FPI examples and Slice 2D HPCA for HPCA examples. And there's also a routine to create 1D plots of slice or cuts through these figures. And that's this crib sheet, which crib sheet demonstrating how to create 1D plots of 2D distribution slices created by that routine. And internally, I think that's shows how to do it using these slices. They're actual slices generated by here. And so what if you want to combine time series plots to, or you want to combine these 2D slices with time series plots? So we have a routine called flipbookify, MMS flipbookify. and essentially turns your current T-plot window into a flipbook style series of images containing the line spectra plots and the 2D slices. And again, we have a crib sheet under the advanced folder that shows more examples, but let's go ahead and show some examples here. So I updated the time range, 9:30 to around 9:34. And we're going to load FGM data, FPI data, and then HPCA data, moments data. And we're doing this to create just a window with various, or T-plot window with various data types that we can then add slices to. I probably should have done a reset session. It's probably taking a long time to load the data because we have so much other data loaded already. It's having to overwrite the data that we already loaded. But I'm going to create a new window with the X size of 1,000 pixels and Y size of 650 pixels, and then create a T-plot window inside that window. Shows the B field on top, the number density, the ion number density, ion bulk velocity, and the ion energy spectra for FPI. And I don't think I used the electron data anywhere, so I probably should have just loaded the ion data. So I'll update that. And again, since we're plotting the data along with the FGM data, we really want to use that center measurement keyword because this FGM data are at the center of the accumulation interval. So you want the FPI and the HPCA data to also be at the center of the accumulation interval. And now it's loaded the HPCA moments. And while it's creating that, we can go ahead and look at the header of MMS Flipbookify. And just like with the other tools, this has lots of options. Most of the options, I think all of the options to the slice routine are also supported by MMS Flipbookify. So you can change, for example, set the slices. By default, it uses 3 slices. And I think the default are XY, YZ, and or XY, XZ, and then YZ from top to bottom. So you can modify these to include any of these other options. And by default, it uses FPI and ion data. And it also uses burst mode by default. So some other options. So you can set the energy keyword. Oh yeah, this is why the 2D slice routine has the energy range specified by E range. There's actually a keyword called energy to the slice 2D routine that tells it to plot energy slices instead of velocity slices. So that's why you have to, there's a difference between MMS part get spec and MMS slice 2D for specifying the energy range. All right, so we created this T-plot window and this other window that we just created. But we're still plotting, notice that we're still plotting 903 to 904 on this day back in December 2016. It's because we used t-limit earlier. So to reset the t-limit, you just give it the full keyword. And so then it uses it updates the time limit to the data that's actually plotted. So now we're in September 2017. And we have our t-plot window. It really doesn't matter what's plotted in here. You can plot everything, plot a bunch of stuff. And then you call MMS flipbookify, and what it does is it'll move the plot over. And so it adds room on the right-hand margin for those slices, and then puts 3 of the slices into the figure. And so in this example, we're specifying the energy range for the slices. We're telling it to use fast survey mode data because by default it uses burst mode data. And we're telling it to put a slice every 10 seconds. And if you don't tell it the timestamp or stamps or the seconds, it'll use every timestamp in the top panel. So now you can see it moved the plot over, and it added 3 slices, and it's drawing a vertical dashed line at each time where the slices are generated. And it also saves these as PNGs in your working directory under a subdirectory named flipbook. So it should be creating PNGs for each one of these times. So we can go ahead and open one of these. And so this is the image on the right at 9:30:10. It has the slices. Again, it's the VX and VY, VX and VC, and VY and VC slices. And notice that the color bar on this bottom spectra is over to the right. This is because of that multi-axis plot that I created earlier. So I should have done a full reset session, and it would have fixed that and wouldn't have put that over there had I done a full reset session before starting here. So if you're manipulating various things on the plots, like the color bar where it's located, I suggest doing a full reset session before creating entirely new figures. And so one of the most important things to note, I mentioned that if you don't set seconds equal to 10 here, it's going to use those timestamps in the top window. And if that's FGM data, it can be very high resolution. So you might end up so the warning here in the notes is that if this happens to be a full day of FGM survey data, you'll create over 1 million plots. So you want to set either the time step or the seconds keyword to avoid this. So you could say time step for 10,000 would be to create 1 plot every 10,000 FGM data points, or seconds equals 6, for example, to create 1 plot every 6 seconds. And so a few other things to note is that you can control most aspects of these figures. For example, setting the thickness of the vertical line that's drawn, do the change of the style. I think that's wrong. I think that's supposed to be an L. Line style of the vertical line at each point. So if you give it a T range, in this case, we said to use the entire time range of the top panel because we didn't specify a time range anywhere. But if you give it a T range, it'll actually draw solid vertical lines around the time range that you requested, and it'll only do the time steps within that time range. And you can also control what that box looks like. You can change the color of the line style of the box, the thickness. And you can also just disable the box altogether with no box. And so there's also options for setting outputting the data or the images PostScript files. So you just set PostScript, and instead of creating PNGs in your flipbook folder, it'll create PostScript files. And you can change the output directory. Again, by default, it just puts it in your working directory in a subdirectory called flipbook. You can append a file name suffix to the files, and you can give it the video keyword to create a video of the images. And it only works for PNG. You can set some of the video options as well. So I mentioned by default it uses FPI. So in this example, next example, we're going to plot HPCA just by setting the instrument keyword to HPCA, setting the data rate to survey, and species to H+. And I also created a new window with some HPCA data just to show that. So you have FGM on top, H+ number density in the middle, and then the H+ ion bulk velocity on the bottom. And again, it's adding slices. Should be every 10 seconds. And the file name of the new files actually has the instrument and the species in it. So you can differentiate between those and FPI files. See, and in this example, we're also limiting the energy range again to 0 to 300 dB. And that should be almost done. Generate a bunch of figures. And now it's done. So for the next one, we're going to plot some more FPI data. And then we're going to change some of the options of the slices. So we're setting the slices. This is essentially the rotations. We're going to make the top figure the BB rotation, then the perp, and then the perp XY. And those match the rotations in MMS part slice 2D. So it's just this one on the top slice, and then perp is this one, and then perp XY is the one just below that. Yeah. It should be FPI again, since we're not specifying the instrument. And I'm also setting the X range and the Y range for the slices. So most of the options are the same, except for the rotations of the slices and the X range and Y range. And again, this color bar that we moved over earlier for the multi-axis plots is going to be overriding some of the axes for the bottom slice. But again, just if you do a full reset session before jumping into here, it'll have that in the right place. And you can see now it's generating these FPI slices, and so the Y range and the X range on the slices is now -100 to +100. So we're zoomed in. And all of the slice options, I think all of the slice options can be passed through to MMS Flipbookify. So for example, you could change the units to flux units. You can change it from velocity slices to energy slices just with the energy keyword. So now we can open one of these PNGs and see we have the vertical dashed line at the time that the slices were created, and then we have the actual slices. So BV is on the bottom. I think that was perp, and then perp XY on top. I think I might have had those backwards earlier. But the first one is the bottom slice. The middle one is the middle slice, and then the last one is the top slice. And so you can see that bidirectional beam in the bottom slice. And so the next one, I'm going to show how to create a video. So again, it's all the same stuff, except in this case, we're giving it the video keyword. So same figure, same rotations in the figure, same FPI data, limiting the energy range from 0 to 300 EV, and fast survey data, and putting the X range and Y range, limiting those to -100 to +100. And so now that it's generating the slices, it also is updating a MPEG-4 file with the new slice, or with every slice. And just like with the other routines, there's crib sheets that show how to So under the advanced folder in the examples, it's just MMS flipbook crib. There should be a bunch more examples. I'm working with this. Including saving as postscript, limiting the time range with the T range keyword, using time steps instead of seconds, and changing the rotations, doing a video, including 1D cuts through the 2D slices. So these include 1D BX and 1D BY. This pushes everything over again and includes another plot that's essentially a sum in one direction. And so if you're interested in adding those, it should be documented in the header. And there's an example in the crib sheet. It's somewhere. I actually don't see it. I might have to update the documentation to include those. But we also have keywords to set those Y ranges and X ranges and their thickness. Looks like we're almost done. Yep. So now that it's finished, we should have this MPEG-4 file. We're going to open. And so here's a video of every slice. Run it and see at each time step, it has the vertical line, the slice was drawn, and you can essentially just watch the evolution of the slices during that time range. And so that's most of what I have for Flipbookify. We could do an entire webinar just on Flipbookify and all of the options. So if you're interested in that, check out the header and the crib sheet and really just try it out. One thing to note is that sometimes you might not have enough room for the slices in your window. So I suggest using this X size and Y size to increase the size of the window to make sure everything can fit. And finally, we have a wrapper called for the IC3D. This is the tool provided by users in Japan to do essentially 3D visualizations of the distribution functions. And so what happens here is call MMS part slice 2D or MMS part IC3D, and it loads the data, loads the support data, and then calls the IC3D tool to visualize the distribution. So in this example, we're loading 30 seconds of data, and then again, just like the other routines, this defaults to HPCA. So if you don't specify an instrument or FPI, you don't specify an instrument equals HPCA, it'll just load FPI data by default and create the figure for FPI data. And there should be options in the header. So you can load the data from SPDF. You can average over a certain time range. You can change the data rate, the level, instrument, and the species, and the probe. And this probably would have been a lot faster had I done a full reset session up here, because we already have so much data loaded. Right, so it should be almost finished. It's loaded the data, now it's creating the figure. And not sure what that was, but now we have an interactive window that shows the distribution function data, and then you can, for some reason it's really lagging. There are options for showing slices, setting ranges. So and you can move around. It's really lagging right now for me, I think, because I'm doing this on a 4K screen and I'm zoomed way in. So I think it's taking a lot longer than it should to move things around. But by default, it shows a volume plot of the distribution data. You can turn it to a scatter plot. It should update. Might have frozen the computer. At least IDL. Yeah, anyway, you can update the access units, the coordinate system, the units. By default, it's just a distribution function. You can output it to a PNG file. And I'll go ahead and close it since it's frozen. Yeah, it's completely frozen. So it shouldn't freeze for you. If it does, send me an email. I think it's just freezing because of the way that my screen is zoomed way in. And I had all that data loaded from before. It's actually the first time it's done that for me. But again, you can do the same thing with HPCA. You just set the instrument to HPCA and the species to H+, and it will show the H+ distribution function. And you can use the tabs here to limit the range. Look at that, I changed the angles. There's a vector tab here that shows what these vectors are. I think the yellow is the sun, and this one is the B field, but I would check the vector tab. It should have it labeled exactly which one is which. This one might be the B field, but it's frozen, so I can't see. So, but that's pretty much the whole webinar. Again, I'm going to put this script. I think we're almost out of time to. This thing's going to end automatically in 8 minutes or so. So I'm going to put this script in the distribution projects MMS examples webinars folder. And the name of it is MMS Plasma Webinar, and then it has the date at the end. So check the date to get the latest version. And it should be in there in a few minutes, right after I remove this webinar or finish the webinar. I'm going to add it and then try to rebuild the bleeding edge so you can download the latest copy today and go ahead and start playing with the script. And again, I mentioned earlier that you can, finally finished. I mentioned earlier that you can download the latest version of the bleeding edge from our changelog, which is just spedas.org/changelog. So, and it's the current bleeding edge can be downloaded here. And so that's all I have. If you have any questions afterwards, feel free to email me. My email is going to be up here. Should also be in the announcement emails. Feel free to email me anytime. It's just egrimes@igpp.ucla.edu. So thanks for calling in.